In 1943, a small machine shop in Woonsocket, Rhode Island, shipped its 797th precision surface grinder. 3 years earlier, that same shop had shipped its 130th. Do the math. In 36 months, while the world was burning, one company in a city most Americans couldn't find on a map produced over 600 precision grinding machines. Not rifles, not shells. Machines that made the machines that made everything else. Who builds something like that? Who even knows how? That kind of precision doesn't come from nowhere. It doesn't come from a government contract or a wartime miracle. It comes from 70 years of quiet, obsessive, unglamorous work in a mill town on the Blackstone River by men who started out sewing fabric and ended up defining what flat means in American manufacturing. This is the story of Taft-Peirce. April 2nd, 1875. Woonsocket, Rhode Island, a city built on water power and textile mills, where the Blackstone River had been turning wheels since before the Revolution. Someone opens a small machine shop and calls it the Houghton Sewing Machine Company. No fanfare, no ribbon cutting, just iron, oil, and the smell of cutting fluid on a cold New England morning. Who was Houghton? History doesn't dwell on him. What matters is what the shop became. By 1876, a young carpenter named Samuel Wardwell had found his way through the door. He hadn't come to sew fabric, he'd come to understand machines. He learned the trade from the inside out, and by 1886, he owned the place. He renamed it the Wardwell Sewing Machine Company, incorporated it properly, and began pushing it beyond the original vision. Under his ownership, the shop wasn't just assembling sewing machines anymore. It was solving problems for other manufacturers, taking on contract work, making parts, building things other shops couldn't or wouldn't attempt. And the man who made that possible was his plant foreman, a machinist named Edwin J. Peirce. Peirce was the kind of man American manufacturing was built on, not an inventor in the romantic sense, not someone with a patent and a dream, but someone who understood tolerance, who understood that the difference between a part that fits and a part that almost fits is the difference between a weapon that fires and one that jams, between an engine that runs and one that seizes. Peirce ran the floor, he set the standard, and he saw something Wardwell perhaps didn't fully see, that the real money, the real future, wasn't in sewing machines at all. It was in precision itself, in the ability to make things exactly right, on demand, for anyone who needed it. In 1895, Peirce acted on that vision. Together with a partner named Daniel W. Taft, he bought the assets of the company outright. The name changed immediately. Taft-Peirce Manufacturing Company. 2 names, 1 idea, that a small shop in Rhode Island could hold tolerances that larger companies couldn't match. But the early years were brutal. The new company tried to be everything at once. They built sewing machines, yes, but also typewriters. And, remarkably, they manufactured the components of a punched card cost accounting system years before IBM made that technology famous. 3 product lines, 3 sets of tooling, 3 sets of customers to chase. It was too much, too fast, on too little capital. In 1903, Taft-Peirce went into receivership. That word, receivership, sounds like an ending. In this case, it was a filter. The men who didn't believe in the company walked away. The men who did stayed and fought. A syndicate of investors moved in by 1905, led by an appointed receiver named Frederick Steele Blackall. He was an engineer, a businessman, and apparently a man who understood exactly what he was looking at when he walked onto that factory floor in Woonsocket, because the Blackall family would run Taft-Peirce for the next 80 years. 3 generations, 1 company, 1 standard. The address, 32 Mechanic Avenue, Woonsocket, Rhode Island. Even the street name felt intentional. By the time Frederick Steele Blackall took control of Taft-Peirce in 1905, the company had already survived 1 death. The question now was what it would become. Sewing machines were a dying game. The market was commoditizing, prices were collapsing, and every small shop in New England was chasing the same shrinking margin. Blackall understood something fundamental. The only way to survive in precision manufacturing is to become indispensable. Not cheaper, not faster, indispensable. The pivot was gradual, then total. Taft-Peirce stopped trying to sell products to consumers and started solving problems for manufacturers. The Contract Service Division, which would eventually become what machinists across America called world famous, was the engine of that transformation. If you had a part that had to be right, if you had a tolerance that couldn't be missed, if you had a job that other shops sent back with apologies, you sent it to Woonsocket. And Woonsocket delivered. But the moment that announced Taft-Peirce to the world didn't come from a gauge or a grinder. It came from an aircraft engine. In 1911, a man named Victor Lougheed walked into the Taft-Peirce factory with a design. Victor was the elder brother of Alan and Malcolm Lougheed, the men who would go on to found what we now know as Lougheed Aircraft Company. Victor was the brilliant, difficult, visionary one, the one who understood aeronautics before almost anyone in America did. And he had designed a V-8 aircraft engine that was, by any measure of the era, an act of mechanical ambition bordering on madness. The specifications were extraordinary. The entire engine was to be machined almost entirely from Krupp chrome-nickel steel, German steel, the hardest and most consistent available anywhere in the world at that time. The crankcase and cylinders were not to be cast in the conventional way. They were to be turned from solid billets. Each billet weighed approximately 2,000 pounds, 908 kilograms, before a single cut was made. The finished engine would have 6 poppet valves in the head of each power-producing cylinder. 8 air pumps projecting from the lower crankcase would maintain constant air compression, assisting cooling on the exhaust stroke. Fuel and lubrication were forced through bypasses in the cylinder walls and pistons themselves. The total cost, $15,000. In 1911, that is roughly $500,000 in today's money. Could any other shop in New England have done this? Could any other shop in America? The fact that Victor Lougheed came to Woonsocket, not to Boston, not to New York, not to Detroit, tells you everything about what Taft-Peirce had already become by 1911. The engine was completed. It was real. It ran. And decades later, Frederick Steele Blackall, Jr., by then president and treasurer of Taft-Peirce, personally donated it to the Smithsonian Institution's National Air and Space Museum, where it sits today. A machine made in a Rhode Island mill town, displayed among the artifacts of human flight. If you want to understand what Taft-Peirce was capable of, you don't need a catalog. You need to stand in front of that engine and ask yourself who built it and how. But the Lougheed engine was a demonstration, not a business model. The real transformation came from something far less dramatic and far more consequential, the go/no-go gauge. A go/no-go gauge is one of the most important and least celebrated tools in the history of manufacturing. The concept is brutally simple. You make 2 gauges for every critical dimension. The go gauge must fit. If it doesn't, the part is too small. The no-go gauge must not fit. If it does, the part is too large. Pass both tests and the part is within tolerance. No measurement, no calculation, no room for human error or interpretation. Binary, absolute, right or wrong. Taft-Peirce became the definitive American manufacturer of these tools. Their gauges were ground and lapped to tolerances that, even today, command respect. Parallel within 0.0001 of an inch, square within 5 arc seconds, surface accuracy of 0.00005 inches per foot. These are not marketing numbers. These are published manufacturing specifications, numbers the company printed in catalogs and stood behind, in an era when most manufacturers wouldn't commit to tolerances in writing at all. Why did American industry accept these as the standard? Because Taft-Peirce had something most companies talked about and few actually had, a policy of publishing their tolerances in print, openly, for any customer to verify. In a world where precision was often claimed and rarely proven, that transparency was revolutionary. You didn't have to trust Taft-Peirce, you could measure them. And American industry, aerospace, automotive, ordnance, toolmaking, measured them, and kept coming back. There is a serial number ledger that tells the story better than any government document ever could. In 1940, Taft-Peirce shipped its 130th number 1 precision surface grinder. That number, 130, represents the entire production run of that machine from the moment it was introduced. Every grinder the company had ever built, up to that point, fit inside that number. Then the war came. By 1943, the serial number had reached 797. By 1945, it was 939. In 5 years, Taft-Peirce produced more precision surface grinders than it had built in all its previous decades combined. The factory floor on Mechanic Avenue didn't just scale up, it transformed. A shop that had spent 40 years building a reputation for quiet, exacting work was suddenly running at a pace that would have been unrecognizable to Edwin Pierce. But here is the question that matters. What were those grinders for? Precision surface grinders don't make weapons. They make the tools that make the parts that go into weapons. They are the machines behind the machines, the ones that ensure a breech block fits its receiver to within a 10,000th of an inch, that a gun barrel is truly cylindrical, that an aircraft engine mount is flat enough to hold alignment under combat stress. When a P-51 Mustang held formation at 30,000 feet over Germany, somewhere in its construction was a part that had been finished on a machine like the ones coming out of Woonsocket. The men running Taft-Peirce during this period were the Blackalls, specifically Frederick Steele Blackall Jr., who had joined the company in 1922, fresh from MIT with a degree in engineering. He was not a soft man. He had served in the United States Navy in World War I, graduating from the Reserve Officers School at Annapolis in 1918. He understood what precision meant in a military context. He understood what happened when it failed. Under Blackall Jr., the company's wartime operation was built around 3 pillars. First, the surface grinders themselves, machines being purchased by arsenals, aircraft plants, and ordnance facilities across the country that needed to maintain tight tolerances on critical components. Second, the gauge production, go/no-go gauges, plug gauges, thread ring gauges, all the measuring instruments that American industry needed in enormous quantities the moment it shifted to war production. When you are making 1,000,000 rifle bolts, every single one has to be within tolerance. You need gauges by the thousands. Third, contract manufacturing, the direct production of precision components for systems the company was never publicly associated with, work that moved through the plant and disappeared into supply chains that led to ships, aircraft, and artillery. There is one detail that survives in the memory of the building itself. One of the factory structures on the Taft-Peirce campus in Woonsocket is remembered by old machinists as the first building in the city to be fitted with automatic sprinkler systems. The reason, according to those who worked there, the work being done inside was considered too hazardous to risk a conventional fire response. What exactly was manufactured in that building has never been confirmed in the public record, but the sprinklers were real, and they were not installed for grinding gauges. What the war taught Taft-Peirce was something that would define the company for the next 5 decades. Scale is not the enemy of precision if you build your systems correctly. The wartime production run didn't produce 600 mediocre grinders. It produced 600 grinders that machinists are still hunting down, rebuilding, and running in their shops today, 80 years later. The quality didn't drop. The standard held. How many American manufacturers can say the same? By the time the war ended in 1945, Taft-Peirce was no longer simply a respected Rhode Island machine shop. It was a proven defense supplier, a recognized standard setter, and a company whose products had touched virtually every branch of American military production. The quiet work on Mechanic Avenue had helped win a war that most of the world hadn't believed America could fight at industrial scale. And Frederick Steele Blackall Jr., the MIT engineer, the Navy veteran, the man who ran the floor through all of it, was about to take that legacy somewhere no one in Woonsocket had expected. In 1953, Frederick Steele Blackall Jr. was elected the 72nd president of the American Society of Mechanical Engineers. Not a regional chapter, not a committee chair, the presidency of the most important mechanical engineering organization in the United States. The body that sets standards for pressure vessels, elevators, pipelines, and power systems that Americans rely on every single day without knowing it. Think about what that means for a moment. The man running a machine shop in Woonsocket, Rhode Island, a city of mill workers and immigrants on a river that most Americans had never heard of, was now the most prominent mechanical engineer in the country. Not because he had founded a technology company, not because he had published a landmark paper, because he had spent 30 years building things right, and the people who built things right recognized him for it. That election was the public signal of something the industry had known privately for years. Taft-Peirce wasn't just a supplier, it was a reference point. When a manufacturer needed to know what flat looked like, truly flat, not approximately flat, they reached for a Taft-Peirce surface plate. When a tool room needed to verify a critical angle, they reached for a Taft-Peirce sign plate. When an inspector needed to check a bore, they reached for a Taft-Peirce cylindrical square. And at the center of all of it was the machine that became a legend, the #1 precision surface grinder. What made the #1 different? On paper, a surface grinder is a surface grinder, a rotating abrasive wheel, a reciprocating magnetic table, a spindle running in bearings. Every manufacturer in the world made surface grinders. The question was always, how good are the bearings? How rigid is the column? How consistent is the spindle under thermal load? How flat is the table after 10,000 hours of use? The #1 answered those questions differently than its competitors. The spindle bearings were carried in solid brass ball and roller carriers, not the phenolic plastic components that other manufacturers moved to as costs rose and shortcuts multiplied. Brass, the kind of material choice that costs more, machines harder, and lasts decades longer. The column was built for rigidity, not for lightness. The table travel was smooth in a way that machinists noticed immediately and remembered permanently. You didn't just use a Taft-Peirce #1, you felt it. The tolerances the machine was capable of holding were, for a manual surface grinder, extraordinary. Surface flatness achievable on a well-maintained #1 runs to plus or minus 0.0001 of an inch, 1/10,000th. That is approximately 1/4 the diameter of a human red blood cell, not under laboratory conditions, not with a temperature-controlled environment and a team of metrologists, in a tool room, on a Monday morning, by a machinist who had been running the machine for 20 years and trusted it the way a surgeon trusts a good scalpel. Why does that matter? Because the parts being ground on these machines weren't decorative, they were functional. They went into dies that stamped aircraft skins, into jigs that held engine blocks during boring operations, into fixtures that positioned gun barrels for final inspection. Every 10,000th of an inch that slipped through on a surface grinder somewhere upstream became a tolerance stack somewhere downstream, and tolerance stacks in aerospace and ordnance have consequences that aren't measured in dollars. Taft-Peirce understood this, and they built the #1 accordingly. The machine's reputation spread the way good tool reputations always spread in manufacturing, not through advertising, but through conversation. One toolroom foreman told another. One plant manager specified Taft-Peirce on a purchase order, and the purchasing department never questioned it again. The #1 showed up in aerospace plants in Connecticut, in automotive tool rooms in Michigan, in ordnance facilities in Pennsylvania, in precision job shops from New England to California. It became the machine that serious shops bought when they were serious about their work. And the company that built it was, by the mid-1950s, operating at the peak of everything it had been building towards since 1875. 3 generations of the Blackall family, 80 years of accumulated knowledge about what precision meant and how to deliver it. A product line that ran from individual gauges small enough to hold in one hand to surface grinders that weighed hundreds of pounds and would outlast the buildings they were installed in. The catalog from this era reads like a document from another civilization. Hardened and ground parallels, box parallels, planer and boring mill parallels, leveling straight edges in cast iron and steel, toolmakers' adjustable knees, adjustable angle plates, universal right angle irons, bench centers, duplex bench blocks, cylindrical squares, sign plates, V-blocks, magnetic chucks in a dozen configurations, surface plates, adjustable reamers, every item listed with its actual manufacturing tolerance, in print, in ink, with no asterisks and no fine print. This was not a company selling hope, this was a company selling geometry. And then, on July 6, 1963, something happened that no serial number ledger records and no catalog describes. Frederick Steele Blackall Jr., the MIT engineer, the Navy veteran, the ASME president, the man who had run Taft-Peirce through a world war and into its golden era, died in a plane crash near Sainte-Félicité on the Gaspé Peninsula in Quebec. He was 66 years old. The loss was real, the kind of loss that hollows out an institution when the person who embodied its standards is suddenly gone. But the Blackall line did not end there. His son, Frederick Steele Blackall III, Yale class of 1945, born in Providence in 1925, had already been working at Taft-Peirce since 1949. He stepped into the role of president and treasurer and then chairman, and he would hold the company together for another 23 years until 1986. 3 generations, 1 standard, 1 address. But outside those walls, the world was changing in ways that no amount of precision could stop. In 1973, imported machine tools accounted for exactly 10% of the American market. 10%, a nuisance number. The kind of figure that gets mentioned in an industry report and forgotten by the time the coffee goes cold. American manufacturers looked at that number and saw a rounding error. They should have seen a warning, because that number was not stable. It was a trajectory. By the end of the 1970s, imports had climbed to 22%. Still not catastrophic, but the direction was unmistakable, and the reason was not simply that foreign tools were cheaper. Japanese manufacturers had done something far more dangerous than undercutting on price. They had matched American quality. In some categories, particularly in the emerging field of computer numerical control, CNC machining, they had surpassed it. And they had done it while American manufacturers were still debating whether CNC was a passing fad or the future of the industry. It was not a passing fad. The Japanese machine tool industry had been essentially destroyed by World War II. By 1955, Japanese machine tools represented just 0.5% of world exports. 0.5%. Within 5 years, Japanese production had risen by a factor of 15. By 1960, American Machinist magazine, the trade Bible of the industry, was already noting that Japanese tools, for the first time, appeared to merit recognition and to be competitive with machines of the most advanced industrial nations. American manufacturers read that sentence, nodded, and went back to doing what they had always done. That was the mistake. The recession of 1982 turned a slow erosion into a collapse. Machine tool sales in the United States fell from $5 billion in 1981 to just $2 billion in 1983. In 2 years, the industry lost 60% of its revenue. From 1981 to 1983, employment in American machine tool manufacturing declined by 35%. 1 in 3 jobs, gone. And unlike previous downturns, where sales dropped and then recovered, this time the recovery never came. Not fully. Not for most companies. By the mid-1980s, 75% of all CNC machines sold in the United States were imported. Japan alone controlled 50% of the American CNC market. The country that had invented numerical control technology, that had developed it in American universities with American defense funding, was now buying it back from Japan at a premium. How does that happen? How does an entire industry lose its own invention? It happens the way all industrial decline happens, not in a single dramatic moment, but in 100 small decisions that each seemed reasonable at the time. American machine tool companies, most of them small and family-owned, struggled to finance the capital investment that CNC development required. Banks that had lent against physical assets for generations didn't know how to value software and electronics. The apprenticeship systems that had produced generations of skilled machinists were collapsing across New England and the Midwest, starving companies of the human capital they needed to innovate. And the strong dollar of the early Reagan years made every American-made machine more expensive on the world market and every import cheaper in the domestic one. Meanwhile, Japanese manufacturers were operating with government backing, long-term bank relationships, and a manufacturing culture that treated precision as a national priority rather than a business variable. They were not just competing, they were executing a strategy, and the strategy was working. The federal government eventually responded, but slowly and without conviction. Voluntary export restraints were negotiated with Japan in the mid-1980s, limiting the volume of certain machine tool categories that could be shipped to the American market. The restraints bought time. They did not buy competitiveness. American manufacturers who had hoped that protection would give them room to modernize found that the underlying problems, capital, skills, technology transfer, management culture, didn't respond to tariffs. Some companies died outright. Others were acquired by foreign manufacturers who wanted their customer lists and their factory buildings, but had no particular interest in preserving what had made them valuable. Brand names that had meant something in American tool rooms for 50 years were stripped of their engineering teams, run for cash, and eventually discontinued. Taft-Peirce watched this happen and made a choice. The choice was not obvious, it was not guaranteed to work, and it required the company to be honest about something that family-owned manufacturers almost never want to admit, that the market they had dominated for decades was changing in ways they could not control, and that survival required becoming something fundamentally different from what they had been. What was that choice, and did it save them? The companies that died in the 1980s American machine tool collapse all made the same mistake. They tried to compete on the Japanese terms. They tried to match the price. They tried to accelerate production. They tried to cut costs in the places that were easiest to cut, materials, inspection, finishing tolerances, and discovered too late that those were precisely the places where their value had always lived. You cannot out-cheap a manufacturer who has government backing, lower labor costs, a weaker currency, and 20 years of accumulated process improvement. You will lose that fight every time. Taft-Peirce didn't fight that fight. What the company understood, and what Frederick Steele Blackall III understood specifically in the years before he stepped down as chairman in 1986, was that the #1 surface grinder was not their future, it was their past. The market for manual surface grinders in American industry was shrinking. CNC grinding centers were taking over production work. The shops that still wanted a manual grinder were increasingly willing to buy a Japanese or Taiwanese machine at half the price for work that didn't demand the last word in precision. Taft-Peirce could not win the manual grinder market on volume. The numbers simply didn't work. But there was something they could win, something the Japanese manufacturers, for all their extraordinary capability in CNC production equipment, had not yet cracked: the metrology market. The precision inspection tooling market, the world of angle plates and V-blocks and sign plates and cylindrical squares and surface plates, the reference tools that every serious manufacturing operation needs not to make parts but to verify them. This market was different from the machine tool market in one crucial way: it could not be commoditized. A CNC machining center is, at its core, a sophisticated electromechanical system. It can be designed in one country, manufactured in another, assembled in a third, and sold in a fourth. The intellectual property lives in software and in process documentation. Given enough capital and enough time, any competent manufacturer can produce a competitive CNC machine. A precision angle plate is different. A precision angle plate is a block of carefully selected, stress-relieved cast iron or hardened alloy steel, ground and lapped to flatness and squareness tolerances that are verified against traceable standards. The value is not in the design. Angle plates have no moving parts and require no software. The value is in the accumulated knowledge of how to select the right material, how to stress relieve it properly so it doesn't move after grinding, how to grind it without inducing thermal distortion, how to lap it to the final tolerance, and how to verify that tolerance with instruments that are themselves traceable to national standards. That knowledge took Taft-Peirce 100 years to accumulate. It lived in the hands and eyes of the men on the factory floor. It lived in the metallurgical specifications developed through decades of trial and documented failure. It lived in the inspection procedures that the Contract Service Division had refined through 100,000 jobs for 100 different industries. It was not transferable by acquisition. It was not replicable by a competitor who simply wanted to enter the market. This was the moat, and Taft-Peirce retreated behind it. The product line that had always included metrology tools, the V-blocks, the angle plates, the sign plates, the parallels, the squares, became the core of the business rather than a supporting element. The contract service division continued to take precision jobs that other shops couldn't handle, maintaining the flow of difficult work that kept the company's skills sharp and its reputation alive. Military and government contracts, which had been a consistent part of the business since the Second World War, continued to provide a base of demand that was insulated from the commercial pricing pressure that was destroying the mass market. The company also understood something about its customer base that many American manufacturers forgot in their panic to respond to Japanese competition. Their customers were not purchasing departments. Their customers were toolroom foremen, quality engineers, metrologists, and manufacturing engineers, people who specified Taft-Peirce by name on purchase orders because they had used the tools and trusted them. These were not price-sensitive buyers in the way that a procurement manager choosing between 10 functionally identical CNC lathes is price-sensitive. These were people who understood what a bad angle plate cost them, not in purchase price, but in bad parts, failed inspections, and scrapped assemblies. When you are building a jet engine component that will be inspected to aerospace tolerances, the angle plate you use to set up that inspection is not a discretionary purchase. It is a critical tool. And the person specifying it is not looking for the cheapest option. They are looking for the option they can defend to their quality manager, to their customer, to the FAA, to the DoD auditor who will eventually walk through their facility and want to know why every measurement in the quality record traces back to a piece of tooling that was purchased from a company with a documented calibration standard. Taft-Peirce had that standard. They had always had it. In a market that was fragmenting and cheapening around them, that standard became a competitive weapon rather than simply a point of pride. Was it enough? In the short term, yes. The company survived the worst years of the 1980s collapse when competitors with larger production facilities and more exposure to the commodity machine tool market went under. The metrology focus gave them a defensible niche. The military contracts gave them a revenue floor. The contract service division gave them flexibility. But survival in a niche is not the same as prosperity. And by the mid-1980s, when Blackall III stepped away from the chairmanship after 37 years of stewardship, the company he handed over was a shadow of what it had been at its peak. Smaller, narrower, still excellent, but excellent in a way that the market was increasingly unable to reward at the scale the company needed to sustain itself. The question was no longer whether Taft-Peirce could hold its standard. It could. The question was whether holding the standard was enough to keep the lights on in Woonsocket. It wasn't. There is a particular kind of institutional death that history finds difficult to dramatize. No hostile takeover, no leveraged buyout engineered by men in Manhattan who had never touched a surface grinder and never intended to. No activist investor demanding the liquidation of the toolroom to unlock shareholder value. No single catastrophic decision that can be pointed to as the moment everything went wrong. Taft-Peirce didn't die that way. It died the quieter, more honest, more devastating way, the way that most American manufacturing institutions of its generation died. It simply ran out of runway. The market it had served so well for so long had changed around it in ways that even the best management couldn't fully compensate for, and when the last member of the family that had kept it alive for 80 years stepped back from the chairmanship in 1986, the institutional will that had sustained the company through receivership and depression and war and foreign competition, that particular human will, was no longer there to hold it together. Frederick Steele Blackall III left the chairmanship in 1986. He was 61 years old. He had spent 37 years at Taft-Peirce, more than half his life. He had watched his father die in a plane crash over Quebec. He had held the company through the worst decade American manufacturing had ever seen. He had made the strategic decisions that kept Taft-Peirce alive when dozens of comparable companies were going under. And at 61, he was done. What happened between 1986 and 1995 is not fully documented in the public record. What is documented is the outcome. On October 6, 1995, the Taft-Peirce Manufacturing Company was formally dissolved. Not sold, not merged, not restructured. Dissolved. The legal word for a company that simply ceases to exist. 120 years. April 2, 1875 to October 6, 1995. From a sewing machine shop on the Blackstone River to a precision metrology institution whose products had touched virtually every significant sector of American manufacturing. Gone. Quietly. Without a press release. Without a Wall Street Journal obituary. Without any of the public attention that the closure of a famous consumer brand would have generated. Because that is how it goes with the companies that make the tools that make everything else. They are invisible to the culture even when they are indispensable to the civilization. No one writes a magazine story about a surface grinder. No one films a documentary about a go/no-go gauge. The work that Taft-Peirce did, the work that made it possible for American industry to hold the tolerances that kept aircraft in the sky and weapons functioning under combat conditions, that work was by its nature anonymous. It was absorbed into the things it made possible and never credited by name. Think about what was lost in that dissolution. Not just the jobs, though the jobs mattered, in a city like Woonsocket that had already lost most of its textile industry and was struggling to define what it was going to be in a post-industrial economy. Not just the buildings on Mechanic Avenue, several of which still stand today as reminders of what once happened inside them. What was lost was knowledge. Irreplaceable, uncodifiable, embodied knowledge, the kind that lives in the hands of a machinist who has ground 10,000 angle plates and knows by feel when the lap is cutting right and when it isn't. The kind that lives in the metallurgical specifications developed through a century of documented trial and error. The kind that lives in the institutional memory of a company that had been solving the hardest precision problems in American industry since before the Wright brothers flew. That knowledge doesn't transfer cleanly. Some of it dies with the people who held it. Some of it survives in the products themselves, in the machines and tools still in service, still holding tolerance, still doing the work they were built to do. Some of it survives in the practices of the machinists who were trained on Taft-Peirce equipment and carried those habits of precision into whatever they did next. But the institution was gone. The address on Mechanic Avenue was silent, and the name that had meant something specific and verifiable and trustworthy in American tool rooms for 100 years, was now available. Someone picked it up. Suburban Tool Incorporated, based in Michigan, had been building precision workholding and inspection equipment for decades. They understood the market. They understood the customer base. They understood what the Taft-Peirce name meant to toolroom engineers who had been specifying it on purchase orders their entire careers. And they understood that a name with that kind of accumulated credibility, a name that traced directly to 100 years of published tolerances and verified precision, was worth preserving. Suburban acquired the Taft-Peirce product line and the rights to the name. They did not acquire the factory. They did not acquire the workforce. They acquired the intellectual property, the designs, the specifications, the catalog, the standard, and they folded it into their own manufacturing operation in Michigan. The products continued. The angle plates, the V-blocks, the sign plates, the parallels, the cylindrical squares, the magnetic chucks, all of it continued to be manufactured and sold under the Taft-Peirce metrology name, now a division of Suburban Tool. The tolerances were maintained, the standards were upheld, the military and government contracts continued, now flowing through Suburban's operation rather than through Woonsocket. Was that continuity, or was it something more complicated, a brand surviving the death of the institution that gave it meaning? Is a Taft-Peirce angle plate made in Michigan by Suburban Tool the same thing as a Taft-Peirce angle plate made in Woonsocket by the men who developed the standard it was ground to? That question has no clean answer. What has a clean answer is the tolerance. The angle plate is either square within 5 arc seconds, or it isn't. The surface is either flat within 0.00005 inches per foot, or it isn't. The standard doesn't care about the address on the shipping label. Maybe that is the most honest thing you can say about Taft-Peirce. In the end, the standard outlived the company. There is a particular kind of institutional death that history finds difficult to dramatize. No hostile takeover, no leveraged buyout engineered by men in Manhattan who had never touched a surface grinder and never intended to. No activist investor demanding the liquidation of the tool room to unlock shareholder value. No single catastrophic decision that can be pointed to as the moment everything went wrong. Taft-Peirce didn't die that way. It died the quieter, more honest, more devastating way. The way that most American manufacturing institutions of its generation died. It simply ran out of runway. The market it had served so well for so long had changed around it in ways that even the best management couldn't fully compensate for. And when the last member of the family that had kept it alive for 80 years stepped back from the chairmanship in 1986, the institutional will that had sustained the company through receivership and depression and war and foreign competition, that particular human will, was no longer there to hold it together. Frederick Steele Blackall III left the chairmanship in 1986. He was 61 years old. He had spent 37 years at Taft-Peirce, more than half his life. He had watched his father die in a plane crash over Quebec. He had held the company through the worst decade American manufacturing had ever seen. He had made the strategic decisions that kept Taft-Peirce alive when dozens of comparable companies were going under. And at 61, he was done. What happened between 1986 and 1995 is not fully documented in the public record. What is documented is the outcome. On October 6, 1995, the Taft-Peirce Manufacturing Company was formally dissolved. Not sold, not merged, not restructured, dissolved. The legal word for a company that simply ceases to exist. 120 years. April 2, 1875 to October 6, 1995. From a sewing machine shop on the Blackstone River to a precision metrology institution whose products had touched virtually every significant sector of American manufacturing. Gone, quietly, without a press release, without a Wall Street Journal obituary, without any of the public attention that the closure of a famous consumer brand would have generated, because that is how it goes with the companies that make the tools that make everything else. They are invisible to the culture even when they are indispensable to the civilization. No one writes a magazine story about a surface grinder. No one films a documentary about a go/no-go gauge. The work that Taft-Peirce did, the work that made it possible for American industry to hold the tolerances that kept aircraft in the sky and weapons functioning under combat conditions. That work was by its nature anonymous. It was absorbed into the things it made possible and never credited by name. Think about what was lost in that dissolution. Not just the jobs, though the jobs mattered, in a city like Woonsocket that had already lost most of its textile industry and was struggling to define what it was going to be in a post-industrial economy. Not just the buildings on Mechanic Avenue, several of which still stand today as reminders of what once happened inside them. What was lost was knowledge, irreplaceable, uncodifiable, embodied knowledge, the kind that lives in the hands of a machinist who has ground 10,000 angle plates and knows by feel when the lap is cutting right and when it isn't, the kind that lives in the metallurgical specifications developed through a century of documented trial and error, the kind that lives in the institutional memory of a company that had been solving the hardest precision problems in American industry since before the Wright brothers flew. That knowledge doesn't transfer cleanly. Some of it dies with the people who held it. Some of it survives in the products themselves, in the machines and tools still in service, still holding tolerance, still doing the work they were built to do. Some of it survives in the practices of the machinists who were trained on Taft-Peirce equipment and carried those habits of precision into whatever they did next. But the institution was gone. The address on Mechanic Avenue was silent, and the name that had meant something specific and verifiable and trustworthy in American tool rooms for 100 years, was now available. Someone picked it up. Suburban Tool Incorporated, based in Michigan, had been building precision workholding and inspection equipment for decades. They understood the market. They understood the customer base. They understood what the Taft-Peirce name meant to toolroom engineers who had been specifying it on purchase orders their entire careers. And they understood that a name with that kind of accumulated credibility, a name that traced directly to 100 years of published tolerances and verified precision, was worth preserving. Suburban acquired the Taft-Peirce product line and the rights to the name. They did not acquire the factory. They did not acquire the workforce. They acquired the intellectual property, the designs, the specifications, the catalog, the standard, and they folded it into their own manufacturing operation in Michigan. The products continued. The angle plates, the V-blocks, the sign plates, the parallels, the cylindrical squares, the magnetic chucks, all of it continued to be manufactured and sold under the Taft-Peirce metrology name, now a division of Suburban Tool. The tolerances were maintained. The standards were upheld. The military and government contracts continued, now flowing through Suburban's operation rather than through Woonsocket. Was that continuity? Or was it something more complicated? A brand surviving the death of the institution that gave it meaning? Is a Taft-Peirce angle plate made in Michigan by Suburban Tool the same thing as a Taft-Peirce angle plate made in Woonsocket by the men who developed the standard it was ground to? That question has no clean answer. What has a clean answer is the tolerance. The angle plate is either square within 5 arc seconds or it isn't. The surface is either flat within 0.00005 inches per foot or it isn't. The standard doesn't care about the address on the shipping label. Maybe that is the most honest thing you can say about Taft-Peirce. In the end, the standard outlived the company. When a knowledgeable machinist finds one in decent condition, the reaction is not nostalgia, it is calculation. These machines, properly rebuilt, are capable of holding tolerances that many modern budget grinders cannot match. The brass bearing carriers that other manufacturers abandoned for cost reasons in the 1950s and 1960s turn out to have been the right engineering decision all along. The rigidity built into the column that made the machine heavier and more expensive to ship turns out to matter enormously when you are trying to hold a tenth over a 12-inch traverse. The decisions that Taft-Peirce made when they built these machines, the decisions that seemed expensive and perhaps overcautious at the time, look like wisdom from the distance of 80 years. Rebuilt. Number 1 grinders sell today for anywhere between $2,000 and $8,000 depending on condition, provenance, and what work has been done to the spindle and ways. For a machine built before 1950, for a machine whose manufacturer dissolved 30 years ago, for a machine with no warranty, no spare parts availability from the original builder, no factory support of any kind. Machinists buy them anyway, because the machine works, because it was built right, because some standards don't expire. The used Taft-Peirce metrology tools, the angle plates, the V-blocks, the sign plates, the parallels, tell a similar story. A set of Taft-Peirce hardened and ground parallels from the 1960s, found at an estate sale or an industrial auction, will typically sell for more than a comparable new set from a budget supplier. Not because of sentiment, because the people who use these tools professionally know the difference between a parallel that was ground and lapped to a published tolerance by people who cared about it and a parallel that was produced to a price point by people who cared about the margin. The market has made that judgment clearly and consistently for 30 years since the company closed. What does Suburban Tool's stewardship of the Taft-Peirce name look like today? The products are real. The tolerances are maintained. The military and government contracts continue. Suburban's Taft-Peirce metrology division supplies precision tooling to military bases and government organizations under active government contracts. Boeing and Northrop Grumman specify Taft-Peirce tooling in their supplier quality programs. Spacex uses it in facilities where the word tolerance is not a manufacturing preference but a physics requirement. The name that Frederick Steele Blackall spent his career building is still, 3 decades after the company that bore it closed, doing the work it was always built to do. Is that enough? Is a name enough when the institution behind it is gone? When the factory is silent and the workforce is dispersed and the accumulated knowledge of 120 years of precision manufacturing exists only in the products themselves and in the fading memories of the men who made them? There is no satisfying answer to that question. What there is, instead, is a measurement, and the measurement is within tolerance. For a company built on the proposition that tolerance is the only thing that matters, that the difference between right and almost right is the only difference worth caring about, perhaps that is the only epitaph that would have meant anything to the men who built it. The standard outlived the company. In Woonsocket, the river still runs. Go back to that number, 797. In 1943, while the world was deciding what it would become, a factory on Mechanic Avenue in Woonsocket, Rhode Island, was running 3 shifts and shipping precision surface grinders to arsenals, aircraft plants, and ordnance facilities across a country fighting on 2 oceans simultaneously. Serial number 797, a number stamped into iron by men who had no way of knowing that the machines they were building would still be running in tool rooms 80 years later, still holding tolerance, still doing work that matters. That number is not just a production statistic. It is a statement about what American manufacturing was capable of when it took precision seriously, when it understood that the difference between a part that fits and a part that almost fits is not a rounding error. It is the difference between a system that works and a system that fails. When it built things not to a price point, but to a standard, when the standard was the point. What happened to that culture? Some of it died in the import wave of the 1980s, when companies that had held precision as a value found that the market would not consistently reward them for it at the margins they needed to survive. Some of it died in the financialization of American industry, in the slow transfer of decision-making authority from engineers who understood what tolerance meant to investors who understood what tolerance cost. Some of it simply aged out, retired, and was never replaced because the apprenticeship systems that had transmitted the knowledge from one generation to the next were allowed to collapse across New England and the Midwest without anyone in a position of authority treating that collapse as the industrial emergency it was. And some of it survived. In the tools still in service, in the machinists who were trained on Taft-Peirce equipment and carried those habits of mind into everything they did afterward. In the companies, Suburban Tool among them, that understood that certain standards are worth maintaining even when the institutions that created them are gone. In the Spacex facilities and the Boeing tool rooms and the defense contractors where Taft-Peirce metrology equipment still sets the reference from which critical measurements are taken. The story of Taft-Peirce is not a tragedy. It is something more complicated and more instructive than tragedy. It is the story of what happens when a civilization builds well, when it accumulates knowledge carefully and embodies it in tools and standards and institutions, and then stops paying attention to what it has built. The knowledge doesn't disappear immediately. It persists in the products. It persists in the people. It persists in the names on the iron. But it erodes, and once it is gone, once the last machinist who learned to feel the difference between a lap that is cutting right and one that isn't has retired and not been replaced, it does not come back easily. It may not come back at all. That is the real lesson of Taft-Peirce. Not that American manufacturing died, it didn't. Not that precision is no longer valued. It is, desperately, in every aerospace and defense and medical device facility in the country. The lesson is that the infrastructure of precision, the companies, the people, the accumulated knowledge, the institutional memory, is fragile in ways that balance sheets don't capture and quarterly earnings reports don't measure. And that fragility has consequences that show up not in the year the company closes, but in the decade after, when the knowledge that lived in that company is no longer available to the industry that needed it. Woonsocket still stands. The brick buildings on Mechanic Avenue still stand. The Blackstone River still runs through the city, turning no wheels now, powering nothing but present, a reminder that the water that drove the first machines is older than any of the companies that harnessed it and will outlast all of them. Somewhere in a tool room right now, in California, in Connecticut, in Texas, in Michigan, a quality engineer is setting up an inspection fixture. They are placing a workpiece against a reference surface. They are zeroing an indicator. They are about to take a measurement that will determine whether a component goes forward into assembly or goes back to the machine. The reference surface they are using may bear a name, Taft-Peirce. They may not know what that name means. They may not know that it traces back to a sewing machine shop founded in 1875 by a man most history books have never heard of, in a city on a river in Rhode Island, where for 120 years people showed up every day and made things right. But the measurement will be right, or it won't. And if it is right, some small part of the reason is a standard set in Woonsocket, Rhode Island, by people who believed that right and almost right are not the same thing. They were correct. If this story meant something to you, if you work in manufacturing, if you use precision tools, if you have ever held a Taft-Peirce angle plate or run a #1 grinder, or simply wondered where the standard comes from, leave a comment. Tell us what you know. Tell us what you remember. The history of American manufacturing lives in the people who made it, and those people are still out there. We want to hear from them. And if you are watching this and you have never thought about where precision comes from, about the companies and the people and the 100-year accumulation of knowledge that makes it possible for a rocket to leave the ground and come back in one piece, think about it now, because the infrastructure of precision is not guaranteed. It has to be built, it has to be maintained, it has to be valued by the people who use it and the institutions that fund it and the culture that decides what is worth remembering. Taft-Peirce remembered. For 120 years, it remembered. The least we can do is remember them.